NASA is planning to land the first woman and the next moon on the moon at the South Pole, which is an area of strategic importance that presents significant benefits and challenges, both related to persistent sunlight and shadows. The role that LiDAR will play in reconnaissance, landing hazard avoidance, and terrain navigation and mapping in aiding exploration of this mission and an eventual one to Mars is essential for everyone to understand. That's why we're thrilled to have Dr. Michael Zanetti, a lunar and planetary geologist from NASA, here to explain it. Dr. Zanetti specializes in comparative planetology, using field investigations on Earth as analogs to better understand geologic processes and features seen in remote sensing data from the Moon and Mars. His current interest is in the use of mobile LiDAR scanning for terrain mapping and navigation, and how ground-based LiDAR can be used as a scientific tool for geology and geomorphology. Please join me in welcoming Dr. Michael Zanetti.
Thank you very much for the very nice introduction. My topic here today is on how we're going to be able to use LiDAR to better understand the lunar surface. And a lot of the talk here is going to be essentially a call to action to the LiDAR community. Because of a lot of the constraints that are placed on spacecraft and landed assets, LiDAR is a really, let's call it, intense data set. And to be able to use it effectively, we're going to need a lot of help. I'm going to start today with a video produced by the Goddard Space Flight Center that's going to take you to the lunar South Pole. Lunar South Pole, like in the introduction, is an area of strategic importance for a couple of reasons. One, there are areas of permanent shadow, and these areas of permanent shadow hold ancient ice that's buried within these very dark regions. It's a stable region where ice can stay. And that is an asset and a resource that can be utilized for a lot of purposes, chiefly drinking water if you're trying to set up a habitat, or rocket fuel. What you're seeing here is a 2-year cycle of the solar illumination conditions at the South Pole. And what you'll see is that they're atrocious. They're really, really difficult. At the South Pole, the sun never rises more than 3 degrees above the horizon, meaning you have persistent, permanent shadows, even from very small objects. But there's also areas of near persistent or permanent illumination. And those are tremendous areas for power resources, for solar power resources. And so with those illumination conditions, it makes it a very challenging environment for exploration. So what you see here are 2 images from Apollo 12, which is essentially our best look at what very low illumination looks like from the ground surface. Apollo 12 landed in the morning and had essentially about 6 degrees of solar elevation when they landed. Again, at the South Pole, it will never get better than 3 degrees. And with that, you've got areas of very long shadows and obviously direct sun. And I don't show them here because they're very difficult to show, are opposition effects, where essentially if the sun is behind you, it washes out everything in front of you and you can't see topography. I'll digress with a really interesting story about Apollo 12 and Surveyor 3. Surveyor 3 is circled there in the image, and when Apollo 12 landed, the astronauts are sitting in the LEM looking at that image essentially out of the window and saying, oh my God, how are we going to get to that Surveyor 3? They were tasked with going and touching this spacecraft that had been landed previously and grabbing parts off of it just to see space weathering effects. But they looked at that and said, how did the scientists get this so wrong? How are we going to be able to get in there? Do we have ladders? Do we have ropes? And that Surveyor 3 is essentially on a 10-degree slope. It is barely perceptible, but it is these really long shadows that make it incredibly difficult for depth perception and spatial awareness. And then there's the other side of the coin, which is direct sun. On Apollo 16, John Young is famous for saying, Driving up sun is murder. It was really difficult for them to plan their missions around the direction of the sun, so they just had to grin and bear it and drive straight through in those terrible illumination conditions. And so, as a LiDAR person, and most of the crowd here are LiDAR people, they can already recognize the advantages that LiDAR are going to be able to bring to lunar exploration from the ground. It's an active source imaging technique. You're basically bringing your own light with you, and you can see into shadow, and you can basically do these high-resolution terrain mapping that we're all aware of. There is long-range sensing potential that is very valuable for these permanently shadowed regions. Part of the reason that there's ice in those areas is because it's incredibly cold, 40 Kelvin cold. And just engineering rovers that can go into those regions, you do need to do reconnaissance in advance. And what we need to do is basically leverage some of the self-driving automotive industry and robotics industries to be able to help address some of that. But that is an upside. That is an advantage that we have at our disposal. But the downsides are pretty scary. LiDAR systems tend to be very power hungry. And the data volumes are immense, and I'll talk about this a little bit later. These are relatively unproven in terms of what we're considering as ground-based assets, self-driving car-like assets. There are no space-hardened variants that are at very high TRL that can be just slotted into place for future exploration. So there are some development costs, and the LiDAR industry is understandably focused on Earth, right? And so we do need to kind of peel off some of that knowledge. So as we go forward here, I'll talk about what I'm doing specifically in terms of using LiDAR to help demonstrate the capabilities and needs for lunar surface mapping. We've developed the Kinematic Navigation and Cartography knapsack with the aim of using velocity sensing FMCW LiDAR hardware to help learn how to explore better using mobile surface mapping. Our system is not nearly as slick as some of the stuff you'll see done on the exhibition floor, but what you see here is an FMCW LiDAR from Ava Incorporated, and an Ouster OS164, coupled with a HG 1700 IMU and GPS. All of this massive headstock that you see above my head there is essentially a development test article to prove out or to better understand how FMCW LiDAR and the velocity sensing capabilities can help improve navigation, orientation, and positioning. So, because I have to answer this to my management all the time, this is not flight configuration, right? We're not trying to take 40 kilograms of kit to the moon. So if you're not familiar with FMCW LiDAR, and or as Ava calls it, 4D LiDAR, it provides you with a Doppler velocity for every point in the LiDAR point cloud. What you see here is some tests that we did just filming a drone landing in a dusty area and watching the plume that got kicked up by it, because in addition to all the navigation and terrain mapping that you can do with LiDAR in general, this 4D capability, this velocity sensing capability, really enhances a scientific aspect that needs to be explored. This is very, very let's call it novel technology for new science. And so what you see in the bottom is red and blue. So these are Doppler shifts. Red is moving away from the sensor. Blue is moving towards it. But as it lands, you'll actually see a rotational vortex from the plume, and that can be measured in and do particle tracking and all sorts of really fun science. But another aspect of FMCW that's really important for us to understand for the moon is its indifference or immunity to solar interference and interference from other LiDARs. So if you're imagining putting more than one asset on the moon, lots of LiDARs looking at each other, very similar situation to self-driving cars on Earth, but also that direct sunlight on the horizon being a challenge. I'll go a little bit more quickly here. This is another test that we did with a rover, basically just showing what FMCW LiDAR technology can see as you're on the ground, following behind people. And it's this ultra-high resolution and high sensitivity to velocity that's really important, not only for being able to track objects, but also in a static scene, you're getting your own ego motion, right? You have very high sensitivity to your own motion without the need for extra sensors like IMUs and things like that. But when coupled with IMUs or wheel sensors, this becomes essentially a single source or a single sensor that allows you to do really accurate orientation for positioning. So you've seen the backpack. What we've done is essentially a bunch of small-scale test areas, again, using areas on Earth to help demonstrate the capabilities of this instrument or these types of sensors, these FMCW LiDAR sensors. This is the U.S. Space and Rocket Center in Huntsville. We're lucky enough to have a rocket park right there near us. And we went and mapped it with our backpack. What you see here in the corner is 3/4 of a Saturn V rocket because, well, that rocket is gigantic. It's 100 meters tall by itself, and we couldn't actually image it with our sensors, or fully image it with our sensors. But we got the Saturn 1B done. One of the really great things that we get to do with these types of data is also public engagement. So this map is actually being used by students for the Human Exploration Rover Challenge. This is a big group of international group where university students build a pedal-powered rover and bring them to this facility. And we can now give them a 3D map for them to work into their simulations. This is the one image that I love to show to my management to show exactly how this can be used on the moon. This is from the Space and Rocket Center, where they have a full-scale mock-up in a lunar crater field, and to show them the power of LiDAR in ultra-high resolution mapping and what you can do to monitor surface assets and also just get measurements of the terrain. It was mentioned in the intro that I'm a geologist and I do planetary analogs. This is one of our most recent tests in November of this year at Kilbourne Hole, New Mexico. This is a volcanic maar, but it essentially looks very similar to an impact crater. And we did a bunch of scanning there in order to map the terrain for astronaut training, geology training of the astronauts. We basically go out there as a precursor, map the terrain, and then we understand it better so that when the geologists go out, or the astronauts go out there, they can better understand the terrain using our data. I'm not going to dwell on this, but we have basically taken our headstock. It's a modular platform, and we've put it on a rover. And I only show this to show that, yes, we are working on the robotic autonomy portion of lunar exploration, but mostly whenever I show the backpack, everybody asks me, why don't you just put it on a rover? Okay, so we did. And what you see there is what our rover is seeing with the dual sensor setup. And just because we also had the opportunity, we suspended our instrument from a crane in order to simulate what it would look like using an FMCW style system for landing hazard avoidance. Yeah, so what you see here is a field of fiducials and us translating the platform through it. So now I guess I'll get to the heart of the matter here and discuss some of the operational challenges of using LiDAR on the moon. I've basically broken it down into two terms that I tend to bandy about. It's see and scrap, and scan and save. If you're only interested in a navigation solution, it's almost a no-brainer to use LiDAR for the lunar surface exploration. You basically can just wander through the scene, use your LiDAR for object identification, hazard avoidance, and terrain, basically just exploration in that regard. But there are important reasons to save all of that data, to build your 3D maps that are then useful for scientists and mission planners and basically just the public too, right? But that is an enormous amount of data. I think most people here who've used LiDAR recognize that these are at least tens of gigabytes per hour, and just getting that data back to Earth is going to be a tremendous challenge. It can't really be done with current technology if you want to save all of your data and beam it back. So now you have to have different strategies of either using dedicated communication equipment like optical communication, or come up with some way for an astronaut to go grab your data and bring it back if it's those tremendous data volumes. But those tremendous data volumes and all of that data is really important for science. I use just a single example here of the Apollo 17 traverse, which is what you see there, that map. That was 3 days worth of driving around in the lunar rover and touring the area. The area that's circled is the rock that you see in this 50 centimeter per pixel lunar reconnaissance orbiter camera data. But what's interesting about that is there's a boulder track. Okay, so the boulder track is this gigantic boulder has rolled down the hill and hit the ground and left big depressions. Scientists want to know what those dimensions of those depressions are. They want to know the morphology of those to back out the energy that was involved in having that rock roll down. And that rock is not small. It's the size of a house. In fact, it's called house rock. But you also want to know the exact morphology of that rock, which can be given to you by ultra-high resolution LiDAR. And so there is a good reason, for a scientific reason, to get all of that ultra-high resolution LiDAR data. But then also just for public engagement and curation. LiDAR already gives you that virtual reality environment that you can overlay all of your subsequent data on. And from the curation aspect, this is where would we have been if we had LiDAR on Apollo? You know, we're 50 years past Apollo, we still mine that data. And moving forward, having centimeter scale maps is essentially a resource that can be used in perpetuity. So my closing thoughts here for challenges for LiDAR on the moon is, well, LiDAR can actually enter a new frontier. Surface-based mobile LiDAR systems or even tripod systems can be incredibly valuable for exploration on and of the surface of the moon. But we do need to strongly consider specific lunar surface concept of operations and mission operation effects or strategies, and they need to be further developed. You know, from the engineering standpoint, questions about power, onboard computation, data storage, transmission, all of these issues need to be thought about and addressed. And there are potential solutions. I didn't mention them, but you know, can we do things like change our mission ops for discontinuous operation of the LiDAR, or better workflows for SLAM to DEM processing, take your point cloud from a massive data set and get it to a picture. Is there ways to do redundant point exclusion or limiting point attributes, all these things that we can probably understand better on Earth in advance, but all will have impacts into the engineering components as well. If you want to do a lot of pre-processing, the computing power on the rover or platform on the moon needs to be done. So I'll leave with a couple of questions here. So how can we use Earth-based advancements in LiDAR and autonomous navigation? How can they be leveraged for lunar use? And conversely, what advancements can we get from solving this scan and save problem for the moon? How can they benefit industry? And so this is my last slide. It's essentially an announcement to the LiDAR industry folks here that there are collaboration opportunities to help address some of the things that I've brought up here. There is the Small Business Innovation Research Fund. These are open now. These are, I think, in the order of $150,000 for 6 month to 1 year collaborations. And it is important, if you're considering one of these, to not get scared off by, let's say, a low dollar amount of 150K. If you have a SBIR Phase 1, it becomes very easy to convert that into a SBIR Phase 3 for long-term engagement and contracting. There are 2 other opportunities that are opening later this week. They are the tipping point and announcement of collaboration opportunities. So please, on February 11th, go find those announcements. And this one's, selfish, but I have a postdoc opportunity available to use the FMCW LiDAR NAC instrument for a lot of these questions, terrain mapping and navigation solutions. And with that, I think we're moving on.